All right, guys, we are going to start chapter 8 with lesson 8.1, similar polygons. Let me present my screen so we can start. All right, so we do have some vocabulary to start with. We're going to do vocabulary a little bit differently for this chapter. Instead of me writing all the terms out on the screen, I'm actually going to use your textbook because I want to make you aware that you do have this feature with your textbook if you didn't know. There is under interactive tools. There is a multi-language glossary, and it's pretty nice because if you need to, let's say, define the first term, which is similar figures, you click on S, then you come down here to the side and look for similar figures. All right, and then you have your definition along with the diagram. You can even click to listen. They'll read the definition to you. But I'm going to have you guys copy the definitions off of the screen here. Write them in your notes, please. If I'm moving too quickly, you can always pause and finish writing the vocabulary before moving on, okay? So similar figures, geometric figures that have the same shape, but not necessarily the same size. Okay, and that's your basic definition of similarity that you've probably heard since you were like in middle school, if not elementary school. Same shape, but different size. Okay, and you have your diagram here that you are welcome to sketch in if you want to, but you don't have to. But make sure you get that vocabulary term written in your notes. Next is similarity transformation. So a similarity transformation is a dilation or a composition of rigid motions and a dilation. Okay, so if you remember back to our chapter on transformations, we talked about translations, remember your slides, rotations, your turns, reflections, your flips, right? And then we did dilations. And your dilations were the only ones that changed the size of the shape, right? It either expanded the shape and made the shape bigger and further away from the center of dilation, or compressed the shape, made the shape smaller and made it move closer to the center of dilation. So a dilation produces a similar figure to the original figure. So that is why a dilation produces a similarity transformation. Now, the other part of it says a composition of rigid motions and a dilation. That just means that you could do a translation and then a dilation, or a reflection and then a dilation, or a rotation and then a dilation, or any kind of combinations of those, as long as there's a dilation involved. If there's not a dilation involved, then you're going to have a congruency transformation. But as soon as there's a dilation involved, again, that changes the size of the shape, so it produces a similar figure. Okay. Corresponding parts is next. Corresponding parts. Now, this is not a new term for us. We talked a lot about corresponding parts when we did our chapter on congruency triangles, congruent triangles. So corresponding parts, a pair of sides or angles that have the same relative position in two congruent figures. Okay. So they listed all the corresponding congruent angles and then the corresponding congruent sides of these congruent triangles. Again, that is not a new term for us. Scale factor. So a scale factor is the ratio of the lengths of the corresponding sides of the image and the pre-image of a dilation. Okay, so you can see here you have your center of dilation, your blue triangle is your original, the red is the new. You can see that the dilation is an expansion. The triangle is larger and it moved away from the center of dilation. And we know, hopefully we remember what that means about what we can kind of guess about the scale factor, the actual value of it. All right. To figure out the scale factor, you're going to put the image over the pre-image. I'll talk more about that as we jump into the notes. Okay. So that is it for our vocabulary. Let me jump on into the notes now. So our core concept, corresponding parts of similar polygons. So we talked about corresponding parts of congruent figures, congruent triangles, but now corresponding parts of similar polygons is just a little bit different. First off, let's get familiar with the notation of similarity. All right, here we have two triangles that are similar, and yes, you could You can write it out as triangle ABC is similar to triangle DEF, but instead of writing the words is similar, we use this little symbol. It's the same symbol we put over top of our equal sign for congruency, but when there's no equal sign underneath of it, it just means similarity. Okay, and you can see it written right here. Triangle ABC is similar to triangle DEF. Now, even if I didn't have the triangles to look at, okay, pretend they're not there. The order of the letters is important, just like they were for congruent triangles, okay? The order of the letters tells me that angle A is congruent to angle D. I know that angle B is congruent to angle E. And I know that angle C is congruent to angle F. Now, the sides are not congruent. The sides are in proportion, okay? And there's a scale factor that we're going to use to map one onto the other. And to write your scale factor, you always start with the new figure is in your numerator, okay? And the original, the old figure in your denominator, okay? So if I was asking, now let me erase all my scribbling. If I was asking, and it kind of is based on the way it's drawing the arrow, right? It's basically saying that this was your pre-image and this one is your image. This is your new. So if I want to know what the scale factor is, I actually start with the new first and I write it as DE, this length right here, DE to BA or AB. All right. If I set up that ratio, that'll give me my scale factor. And that ratio is going to be the same as EF to BC. And finally, DF over AC. And again, I can get the order of the letters by the statements or by looking at the diagram. Now, all of those ratios are going to simplify down to the same value, and that is your scale factor, which we use the variable K to denote the scale factor. Okay, so let's jump into the first problem after I gave you all that information. All right. So it says in the diagram triangle, RST is similar to triangle XYZ. So right away, I could go around and mark angle R is congruent to angle X. And sometimes it's good to do this to make sure they're oriented the same way. Angle S is congruent to angle Y. So 2 arcs there. And angle T, 3 arcs, is congruent to angle Z. Okay, so they are oriented the same way. All right. Also, another trick in case they're not oriented the same way, and in case the similarity statement's not given, how you match up the sides, and I'll talk more about this when I see a problem that this happens. You pick the small side and compare it to the small side. Then you're going to pick the medium length side and compare it to the medium length side, and then large side, large side. Okay, so again, I'll explain that when we see a problem set up that way. All right, so we want to know what is the scale factor from RST to, so think of it as this. This is my pre-image. This one is my image. What is the scale factor that maps this one onto this one? So I want to know, what do I have to multiply these values by so that they equal those values? What do I have to multiply 25 by so it equals 15? So to do that, I'm going to set up my ratios, okay? So I'm going to start with the sides of this triangle. So I'm going to start XY, and XY matches with RS. All right, and that's equal to YZ, which corresponds to ST, and then ZX corresponds to ZXTR. Now I'm going to fill in all the numbers, right, instead of the letters. So I have 12 to 20 is equal to 18 over 30, which is equal to 15 over 25. Now let's simplify all of those. 12 and 20 share a common factor of 4. So it would be 3 over 5 if I simplified. 18 and 30 share a factor of 6. So that'll also be 3 over 5. And 15 and 25 share a factor of 5. That is also 3 over 5. So the scale factor is 3 over 5. And I could double check if I want to grab my calculator and make sure I calculated it correctly. Oh, let me do this. Okay, remember, you're taking, let me quit that. You're taking this number 25, multiplying by the scale factor 3/5. Oh, I'll pull this up, sorry. 3/5. And you should get the side length that it corresponds to. Okay, I could check again. 30 times 3/5. I should get 18. Uh-oh. 3/5. There we go. Uh-oh. What happened? Did I push clear? Oh my goodness. There we go. 18. Okay. All right. So I know my scale factor is 3/5. Okay. All right. What do I want to do next? I'm going to erase some of that because I kind of expanded further than I should. All right. So this is 3 over 5. Now, keep in mind, if they had asked, what's the scale factor that maps this one onto this one, right? So if I was going this direction, then my scale factor would have been 5 over 3. Okay, so just keep that in mind. All right, list all pairs of congruent angles. Okay, we already had marked them, but now I'll list them. And I'm actually just going to look at the letters up here. I'm not even going to look at the diagram. So angle R is congruent to angle what? Angle X. And angle S is congruent to angle Y. And angle T is congruent to angle Z. Okay. And then write the ratio of corresponding sides in a statement of proportionality. That's actually what I had written up here before I erased it, right? I should have just written it down here. Okay. So that long statement comparing all the corresponding sides to one another. And again, you can use the order of the letters here. And it doesn't matter which triangle you start with. So maybe just to do something different than I did above, I'll start with the triangle on the left. I'll start with this triangle. So side RS corresponds to side XY, and side ST corresponds to side YZ, and side RT corresponds to side Z. It's a Z. Okay, and set them equal to each other. This is what we call a statement of proportionality. It's a big extended proportion comparing all the corresponding sides. And they are equal to each other. Remember, they're going to simplify down to the scale factor, or in this case, the reciprocal of the scale factor. They would simplify down to 5 over 3 if I was to fill in the numbers. But that's not what this part of the question is asking you to do. Okay. All right, so that was example 1. Let's move on to example 2, or the next bit of information first. Corresponding lengths in similar polygons. If two polygons are similar, then the ratio of their corresponding lengths in the polygon is equal to the scale factor. Okay, so what that means is you can pick any corresponding sides that you know the length of and simplify them and get the scale factor. You don't have to know all 3. Okay, so since you're told that the 2 triangles are congruent, that means that side DE, which is labeled as 15, right, the first and second letter, that maps onto and matches with this side here, which is 18. So I can just set up 15 over 18 and simplify to get that my scale factor, both are divisible by 3, 5 over 6. My scale factor is 5 over 6, okay? Or maybe instead of picking those 2 sides, I could have picked this side here and this side here. All right. And I could have set it up as 24 over 20 instead, but I'll just stay consistent with how I did the first one. So 20 over 24, both divisible by 4, 5 over 6. Okay. So 5 over 6 is your scale factor, or 6 over 5, depending on how they state, which triangle was the pre-image and which was the image. But you can use the 5 over 6 to set up your proportions to solve for your unknown, or you can use the original value. So I'll show you 2 options, okay? So I could set up a proportion saying 15 over 18 is equal to, 15 over 18 is equal to X over 30. I could have also set up a proportion, 20 over 24 is equal to X over 30. Or I could use the simplified, right? I could simplify each of those down to 5 over 6 is equal to x over 30. There are other proportions that you could set up that are equivalent to the ones that I have set up, but any one of these three will work. Once you have a proportion, you're going to cross multiply. If you use the scale factor, the simplified ratio, it's going to give you the easiest numbers to work with. So I have 5 times 30 is equal to 6 times x. Uh-oh, I ran out of room. That's an x there, okay? 5 times 30 is 150. 150 is equal to 6x. Therefore, x is equal to 25. Okay? All right. Example 3. Triangle TPR is similar to triangle XPZ. Find the length of PS. Okay, well, if the two triangles are similar to each other, that means that this altitude is going to be proportional to this altitude. And that's what you're asked to find for, or solve for, excuse me. So I'm going to put an X. Okay. So just like I did in the example above, I could say that this side of the triangle, which is 12 units long, corresponds to this side of the triangle, which is 16 units long. And that's going to be equal to the altitude of this triangle, which is x, over the altitude of this triangle, which is 20. Again, that is not the only proportion. Instead of using 12 and 16, I could have just used this piece here. And I could have said 6 over 8 is equal to x over 20. That one would work as well. Okay. And there are others that you could set up as well. Okay. But one of these, I'm going to choose the one with the 6 and the 8 just because the numbers are smaller and easier to work with. Cross multiply. So I have 8x is equal to 120. I'm going to divide both sides by 8 and get x is equal to 15. All right. Any questions on that one? Okay. Perimeter of similar polygons. Okay, so this theorem and then the next are similar to each other. So I'll probably read both theorems and then do problems 4 and 5. Okay, and then that'll be it. All right, so this theorem, and it's very, very, very helpful to remember these two theorems. This theorem tells us that our ratio of perimeters is equal to your scale factor. Okay, so even if you don't know the perimeter of one of these figures, if you know the scale factor and you know the perimeter of one of the two figures, you can solve and find the perimeter of the other figure. And that's what we're going to do below. Okay, the other theorems, let me just jump down there so I can write it in words like I did above. This theorem tells us that our ratio of areas is equal to the scale factor squared. Okay, if you square your scale factor, then that's equal to the ratio of areas. So again, if you know your scale factor, and let's say you know the area of this figure here, you can solve for the area of this figure here without even knowing all the different dimensions of the actual figure. As long as you know the scale factor and the area of one, you can solve for the area of the other. And you'll see that in the example 5. Okay, so example 4. It says a town plans to build a swimming pool. Okay, an Olympic pool is rectangular with a length of 50 and a width of 25. So this right here, this is your Olympic swimming pool that's already built. The town wants to build this new pool, and it's going to be a similar shape. So again, it's going to be a rectangle, but it's going to have a length of 40 meters. So I'll sketch, this is my new, and it's only going to be 40 meters. And I don't know this dimension here. Okay. Now, remember what I said? Oh, by the way, it says find the perimeter of the Olympic pool and the new pool. Okay. So let's find the perimeter of the Olympic pool because we can, right? We know all the side lengths. So perimeter of Olympic. So you take 25 plus 25 plus 50 plus 50, or 2 times 25 plus 2 times 50. Okay, so when you add those all up, you get 50 here and 100, so it's 150 meters for the perimeter. Now, could I solve for the missing side here using proportions? And then once I know that side, could I just add all the sides up together and know the perimeter? Absolutely. I'm not going to do the problem that way just because I want to show you another option. Maybe I'll do it that way second. All right. So I'm going to ask you, do you know the scale factor? All right. You do. You can figure it out. The scale factor. All right. Remember, the scale factor is your image over your pre-image. So your new over your old. The scale factor is 40 over 50, which simplifies down to 4 over 5. Now, the theorem above says that your scale factor is equal to the ratio of perimeters. So my scale factor has to equal the ratio of the perimeters. Well, I know the one perimeter of the Olympic pool, the larger pool, is 150 meters, but I don't know the perimeter of the other pool, the new pool. But now I have a proportion I can solve. If I do my cross products, I'm going to have 5x equals 4 times 150. What is that off the top of my head? That's 24, 5, 6, 600, I think. All right. And then you're going to take 600 and divide by 5. Just want to make sure my math is correct. Yeah, 120. Okay. So you get x equals 120. And now you know that your new pool has a perimeter of 120. Now, just to show you that you do have another option, okay, so if I wanted to, I could have solved for x here. I could have said 50 to 40 is equal to 25 over x. 50 to 40 is equal to 25 over x. When I do my cross products, so that's going to be 40 times 25, which is 1,000, equals 50x. Divide 1,000 by 50 to get x is equal to 20. Now that I know that this side is equal to 20, can I find the perimeter by just adding 20 plus 20 plus 40 plus 40? And isn't that going to equal 120? Yeah. Okay. So that's your other option. But that's not what I wanted to show you because that didn't use the theorem we just talked about. Okay. All right. And the last problem, problem 5. So again, the scale factor squared is equal to the ratio of areas. I know the area of this triangle. I don't know the area of this triangle. And I can't just use area equals 1/2 base times height, right? I can't use the area of the triangle because I don't know enough about the triangle. I don't know all the dimensions needed. So what I'm going to do is I'm going to first look for my scale factor. Okay. I don't really know which one was the original and which one is the new. So it doesn't really matter how you set up the scale factor for this problem. You could do 5 over 10 or 10 over 5 and you'll still get the same answer in the long run. I'll do 5 over 10, which we know simplifies down to 1/2. Now, if I square that scale factor, it's going to equal the ratio of areas. Okay. Well, I know the one area, but I don't know this area. That's my unknown. All right. So first, let's square 1/2. Square the top, square this bottom. You get 1/4 is equal to the area of the larger is 36. I don't know the area of the smaller. So I square my scale factor and set it equal to the area, the ratio of areas. Now it's just cross products. Cross multiply to get 4x. Cross multiply to get 36. Divide both sides by 4. You get x equals 9. So I just found out that the area of this smaller triangle is 9 centimeters squared. Okay. All right, guys, I believe, let me just check my notes real fast. Yes, that was it. Okay, guys, that is it for lesson 8.1. I'll see you back here for lesson 8.2. Bye.